Hi, I'm Rob Jackson, student RLJ613 in the Science and Cooking course at Harvard. And I'm going to talk about a modification to the recipe for a perfect egg shown in the introduction to Lab 2. That recipe calls for weighing the egg, using the equation of the week to calculate the number of joules it takes to cook the egg, using the same equation to find out how much boiling water would need to be added to provide those joules, and then putting the water with the egg in an insulated container and waiting until the energy transfers from the boiling water to the egg to cook it. There are some problems, however, in using this recipe with a thermos or some other container that's readily accessible. First of all, that the container itself has to be heated, and second, that the container is not going to retain the heat perfectly, and these losses have to be calculated. I've used what we've learned in this course to compensate for these losses by the following process. First, we determine the amount of time that it takes to cook an egg, and then the amount of energy it takes to heat the thermos for the amount of temperature that we need and the duration of cooking of the egg, which I call Q of X for any delta T change in temperature. And finally, we determine how much heat gets lost versus the amount of heat used in cooking. Ratio of X is useful for that. It takes the amount of overall heat added for cooking an egg versus the heat that is actually used in the cooking of the egg itself. Armed with these two things, we can then modify the approach from above. First, we calculate the number of joules to cook, as we did before for the egg itself, but then we multiply that by our ratio, and we add Q of X, and then we calculate boiling water in the same way, and this time we wait until the time X before we finish the cooking. Materials needed include, of course, a thermos. I bought a cheap one, and a digital scale, a hot water heater, this one is coil-based, some sort of thermometer, and of course a computer. We learned about two ways of determining cooking time in our course. I'm using the first one, which is a random walk based on the equation of the week, which determines how quickly something, in our case heat, diffuses into something else, in our case an egg. You can solve for T and then plug in values for L and D. L is the distance that the heat has to travel before the egg is fully cooked. Now, the mouth of my thermos only accepted a 4.5 centimeter egg in diameter, so I found that the eggs that I used tended to be about 4 centimeters. I halved that to find the radius, which is 2 centimeters. The diffusion constant I borrowed from the lecture in week 6 based on the diffusion constant for heat going into a water-based food such as meat, or in our case an egg, and solving for T I got 25 minutes. A more precise calculation could be determined using the advanced materials from week 6 using Newton's law of cooling, which unfortunately I currently lack the mathematical knowledge to be able to implement. I tried the applet My Meat without success because My Meat is based on a surface cooking area versus cooking something spherical from all around. I used the specific heat for eggs and for water from the course itself from week 2, but you can go to this site or many like it to find specific heats for any type of food that you want. To determine the amount of energy needed to heat the thermos, I effectively reversed the approach suggested in the recipe. I added a certain amount of boiling water, waited 25 minutes, measured the temperature of the water at that point. From that I determined the delta T, and retroactively I figured out how many joules would have been required. And then I used what's called regression to determine the function Q of 25 by going to a site. I simply pasted in 2 columns from my spreadsheet containing delta T and joules, and the regression gave me a formula for the function where X is delta T and Y is joules. My original data is shown here in blue, and the regression function is shown in green. Here's the function implemented in VBS, which I was able to use directly in my spreadsheet. To determine the ratio for cooking loss, I measured a certain amount of food. Water was what I used because it was the simplest. I determined a target temperature to cook the water to, calculated the joules that it would require, and then I found out through experimentation how much I needed to add, and I came up with roughly 18%. The system is not only successful, it's amazingly robust considering that my thermometer only measures to a degree Celsius. I was able to reproduce all of the phases on Dave Arnold's chart the first time, with the exception of 65, which took a second time. Not only that, I'm able much more easily than I thought to identify the phases properly. For instance, this 64-degree egg has a yolk that has partially set, but is partially liquid, in contrast with a 63 egg, which is entirely liquid, and the 65 yolk can be shaped into a heart. This is about far more than making eggs. It's about emulating an immersion heater using a $10 thermos with the help of a few equations of the week. In order to capitalize on that potential, we need to be able to approximate Q for values other than 25. And to do that, I created a second baseline by experimentally deriving values shown in blue for Q of 10, and the regression for that is shown in purple. And you can see that the two functions, Q10 and Q25, grow very much in parallel up to about 50 degrees. But bear in mind that that is delta T. You have to add the ambient room temperature, which is about 20 degrees Celsius. So really we have here a period up to about 70 degrees Celsius, for this thermos anyway, where the two are very closely related to each other. And you may recall that most proteins denature between 50 and 70 degrees, as we learned in the course, and therefore that range for cooking is safely contained within this area where the two functions grow in parallel, which means that approximation shouldn't be too difficult and should be fairly accurate. In short, my advice for anyone creating a mock immersion heater is first, get hold of the best thermometer that you can. Second, derive two baselines for approximation. Third, make sure to calculate very precisely all of the cost of cooking something, including, for instance, a sous vide bag. And finally, use the baselines for estimating Q of X and ratio X. I view this as a new type of cooking, which I could call insulated minimal heat, IMH. An immersion heater could be seen as continuing a time-honored tradition of cooking something by placing it into a controlled temperature until a desired phase transition occurs. Not so with IMH. Here we are fundamentally changing the way that we cook, and it could be called perfect in the sense that there's minimal energy consumption and no overcooking. And I think that it has tremendous engineering potential for changing the way that we cook. At this point, software is needed to guide people through this process. And toward that end, research into how Q of X and ratio of X grow with respect to X could greatly simplify implementation. Also, applying Newton's law of cooling instead of random walks would improve the accuracy of cooking times, which is crucial to the calculations. Finally, if you happen to be an engineer and you're interested in teaming up, please contact me. We could be able to create a new type of kitchen appliance.